Okay, so section 21.2 is about unsaturated hydrocarbons. Remember, hydrocarbons contain only carbon and hydrogen, and the saturated hydrocarbons have a maximum amount of hydrogens. And so unsaturated hydrocarbons, we'll see that they have fewer. The first class are the alkenes. Now remember, alkanes with an A were saturated hydrocarbons. Alkenes are hydrocarbons which have one or more carbon-carbon double bond. So they're defined by having a carbon-carbon double bond. They've got fewer hydrogens, and so they're called unsaturated. If you think about it, each of these carbons now, each of these carbons is going to have one extra carbon-carbon bond. This carbon on the left is bonded to the carbon on the right. Carbon on the right is bonded to the carbon on the left, and so you lose 2 hydrogens for every double bond. An alkene that has only one double bond would have a formula of CnH2n without the +2. And if you have more than one double bond, then who knows what that ratio will be. It will go down from there as far as the number of hydrogens. The alkene carbons are going to be sp2 hybridized. That unhybridized third p orbital is what participates in the pi bond or the double bond. This is going to make it trigonal planar in its molecular geometry and bond angles of 120 degrees. So the alkenes, at least around the double bond, are planar molecules with 120 degrees. Alkenes are named just like the alkanes, but with ene at the end of its name. So let me put up some examples. So ethene here, C2H4, is just 2 carbons double bonded. Ethane was 2 carbons single bonded. Propene, C3H6, is 3 carbons with a double bond between 2 of them. And once we get beyond propene, we need to start being more specific about where that double bond is located. So you see the next two, 1 butene and 2 butene are both C4H8. They're both sort of that longest chain of carbons is 4, and so it has that bute primary name. It's got the ene because there's a double bond, but where that double bond is located is different between them. So in 1 butene, you see the double bond begins on the first carbon. For 2 butene, the double bond begins on the second carbon. And so you'll always number your carbons such that the double bond is as close to the beginning as possible. So for example, there's no such thing as 3 butene. If you had the double bond starting on that third carbon going to the fourth carbon, then that would actually just be 1 butene looking from the other direction. You know, things can get a little bit more tricky. So one of my favorite molecules and let me just fill this out with hydrogens. Might as well. But we need 2 hydrogens here, 1 hydrogen, and 2 hydrogens there. Okay, so what is, oops, you can't see it all. Alright, so what is this molecule here? This would be 1,3 butadiene. Okay, where because there are 2 double bonds, we need to put 2 different positions. One of them starts on the first carbon, one of them starts on the third carbon, And then because there are two double bonds, we also need that di in there to indicate that there are two double bonds. So 1,3-butadiene, for example. I won't give you overly complicated problems like this in the exam, but you will eventually learn how to name complicated molecules like this. So alkenes can undergo addition reactions. Let me advance the slideshow a bit here. Oops. Back up. Okay. Make sure you can see it. So when alkenes undergo reaction with, say, bromine or chlorine or fluorine or iodine, it's a very different reaction than when alkanes do. And that's because this double bond is going to be able to interact with that halogen differently. So you'll notice here, if you react ethene with bromine, you end up with 1,2-dibromoethane. The double bond is broken and sort of converted into a single bond, right? And then both carbons will receive a bromine. Sometimes we say this is addition across the double bond, because 1/2 of the bromine molecule is on carbon 1 and 1/2 of the bromine molecule is on carbon 2. So that's if you react with a bromine, or chlorine, fluorine, or iodine would be the same. If you react with something like hydrobromic acid, hydrochloric acid, or hydroiodic acid, the same thing happens, only this time half of the addition molecule is a hydrogen. So your ethene now becomes 1-bromoethane. You can see highlighted there how the new hydrogen and the new bromine came from the HBr. The double bond becomes a single bond. You can even add water across a double bond, and in this case there's a hydrogen added on one side and then the OH is added on the other side. The bond happens through the oxygen. You perhaps know that this is an alcohol. In fact, this is ethanol, perhaps the most popular of the alcohols. This reaction would require catalysis, usually via acid. And then one last addition reaction, you can use hydrogen, and so this would require a heterogeneous catalyst, something like nickel, and that will add across the double bond to just make a plain old alkane. You may maybe have heard of, well, never mind. I won't get into that. Never mind. I was going to get sidetracked, but I won't. All right. So those are what we call the alkanes. Okay, there's one more. Oh, no, there are two more. Sorry. Two more types of hydrocarbons that we're going to look at. So alkynes with a Y. Alkynes are hydrocarbons which contain one or more carbon-carbon triple bond. So because of the triple bond, the alkynes are even further unsaturated. With only one triple bond, you would have CnH2n minus 2. You lose 4 hydrogens to that triple bond. And of course, if you had more than one triple bond, then the number of hydrogens would go even further. So this is a further unsaturated hydrocarbon than even the alkenes. The carbons in alkynes are sp hybridized. That means that these are linear molecules and they have 180-degree bond angles. The alkynes are named just like the alkenes, but they end in "-ine", and their bond position is numbered exactly the same. So let me draw a quick one. We won't spend a lot of time. If I have carbon, carbon, triple bonded to carbon, carbon, carbon. What is this? Well, I count 1, 2, 3, 4, 5 carbons. Contains a triple bond, so this is pentyne. And the triple bond is closest to this end, so I'll count 1, 2. The triple bond starts on the second carbon, 2-pentyne. And if we wanted to fill in the hydrogens here, no hydrogens for these two. There we go. Filled them up with hydrogens. So alkynes can undergo the same sorts of addition reactions that alkenes can undergo, with a few additions. Oop, there we are. So you can add 2 pairs of atoms across that triple bond. Essentially, you would first add 1 bromine molecule and convert that triple bond to a double bond, and then you add the other bromine molecule across that double bond. And so ethyne plus 2 bromines will become 1,1,2,2 tetrabromo ethane. And you can do the same thing with hydrogen, right? So ethyne plus 2 hydrogens becomes just plain old ethane. And those are the alkynes. Alkynes have triple bonds. So the last category here are the aromatics. So aromatic compounds have a kind of a colorful name here. They're called that because actually a lot of these compounds do have a smell or an aroma. But technically an aromatic compound means that you have delocalized pi bonds. You may recall from 1210 that if you have double bonds and single bonds alternating, then the electrons are actually shared across all of the pi bonds that are in that compound. And we call this phenomenon delocalization. So the prime example of an aromatic compound would be that was pretty good. I often draw really badly proportioned hexagons here. This compound is called benzene. And I spent all that time drawing benzene. I'll get out of the way so you can admire it for a moment. You can see that all of these carbons are sp2 hybridized. They all have an unhybridized p orbital, and you may recall from 1210 that leads to resonance structure where the double bonds are drawn in these positions instead of where I've drawn them. And the hybrid structure would just show double bonds all around. Organic chemists get tired of drawing all of these carbons and hydrogens, and you can just go like that to represent a benzene ring, and any chemist anywhere will know exactly what you're drawing. Benzene and its derivatives are examples of aromatic hydrocarbons. So the double bonds here in aromatic hydrocarbons do not undergo the same types of addition reactions that alkenes undergo. And that's because in those addition reactions, you may recall that the double bond is converted to a single bond. If we were to convert this to a single bond, that would disrupt the delocalization in benzene, and it would be very energetically unfavorable to do that. And so these double bonds are special double bonds. They're much harder to break. However, you can have halogenation reactions like the alkanes do. You could replace this hydrogen with a bromine, for example, plus hydrobromic acid by reacting benzene with bromine. And so this leads to substituted benzenes, and again I'm advancing the slides here. There we are. This will be the last thing we talk about today. So if I have two bromines substituted onto a benzene ring, there are three different ways that I could have those two bromines. They can't occupy the same carbon because three of the carbon bonds are already taken up in the benzene ring structure itself. So the bromines are either going to be adjacent to each other, removed by one, or opposite to each other. And you can name these 1,2-dibromobenzene. Let me use my head here. Okay, 1,2-dibromobenzene, 1,3-dibromobenzene, and 1,4-dibromobenzene. Just kind of like we've been doing before, where you number your carbons from 1 to 6. But it's also very common to use this other nomenclature where if the two substituents are adjacent, then it's called ortho-dibromobenzene, or even shorten that to just O-dibromobenzene. If they're separated by one position, then that's meta-dibromobenzene, or just M-dibromobenzene. And then opposite each other is para. So para-dibromobenzene or p-dibromobenzene. And this would be a nomenclature you could use regardless of what sort of substituents are substituted into that benzene ring. So if you had a bromine and a fluorine, then it could be ortho-bromofluorobenzene, or meta-bromofluorobenzene, or whatever it may be. So ortho, meta, and para are very common, and you should be familiar with them as well. So we'll end with that today.